Hello, good evening all. Am I audible?
Yes, sir.
Sorry.
Yes, sir, you are audible.
Thank you for coming. Good evening, I am Saurabh and I welcome all of you to this live session for the course NPTEL course Advanced Thermodynamics and Combustion. Okay, so this is a 12-week course. As you might have already seen the content and course detail. And this is the live session. And in the live session, we try to interact in the live mode because you know that the lectures you are getting each week, they are already recorded. So if you have any query, any doubt or any suggestions, then it is very difficult, or I mean, there is no provision to make changes on those recorded lectures. Okay, so whatever queries you have or whatever suggestions you have, or if you face any problem while solving assignments or any general discussion that you need, that we should discuss, that we can discuss in these live sessions. Okay, so since these are live sessions, so I request everyone to make it, I mean, really live. Okay, so whatever question or anything you have, you can just unmute yourself and ask. Okay, so before we begin, can we please have a quick introduction so that I can get a brief idea that what are your objectives, what you want from this course, so that we can decide a direction for these live sessions. Okay, so you might have already watched the lectures. So are they really serving the purpose you joined the course with, or you need some modifications or some suggestions that you can tell? Okay, so can you please introduce yourself one by one so that we can have an idea? Okay, so what exactly you are studying and what you want that should be discussed in these live sessions. Okay, so can we have a little introduction one by one? We have others, AM, Chandan Kumar, Digant, and Gauravi, and someone else named S. Hello.
Yeah, good evening, sir. Can you hear me?
Yes, I can hear you, others.
Yeah, I am Adarsh Shayan. I am from Kerala. Actually, I am working in ISRO, and uh, I'm doing a PhD course. So for that purpose only, this course I have selected. And
Okay.
my subject is maybe some transient filling of a cryogenic feed line and some related aspects.
Okay, okay, very
So
interesting. Which institute you are affiliated with?
I am doing in Indian Institute of Space Science and Technology, Trivandrum.
Oh, okay, okay, got that, got that. Okay, thank you.
Yeah. Okay. Okay. Fine. Thank you.
And we have Chandan. Can you please?
Yes, hello.
Hi, hello.
Yes, good evening, sir.
Good evening, sir.
I am Chandan from Bihar. Currently, I am MTech first year. So, this course is allotted for MTech online classes, NPTEL certification.
Okay,
Yes.
thank you. We have Digant.
Good evening, sir. Myself, Digant Mehta. I am a faculty member in Government Engineering College, Gujarat. Am I audible?
I think we can't hear you, Digant.
Hello. Hello.
Sorry, we can't hear you, Digant. I think there is some technical problem maybe. And we have Gauravi.
Hi, sir.
Hello.
I'm Gauravi and I'm from Mumbai here, and I'm currently pursuing, I'm a third year mechanical engineering student in VJTI.
Okay. And we have someone else named as I can't read the full name. Okay, so I can't see the full name of, I think one more participant is there. But anyways. Okay, so I think we can now start the session. So today I have kept very basic questions. These are like revision of the content of week 1. Okay, and also some questions, actually questions only, right? So if you had any problem while watching the lectures, if you have any query that you can ask, or maybe you might have solved the assignment. In the assignment, you might have faced any problem that we can discuss. If there is no problem, that then we will continue with these questions. Hello. If there is any query, you can unmute yourself and ask, or we will continue with these questions.
No doubts from my side yet.
Okay. Okay, so I think we. Okay, so we can start these questions. So question number 1 says, which of the following is an example of macroscopic coordinate? So in the lectures, we have discussed about microscopic coordinates and microscopic coordinates, right? So the macroscopic coordinates, they,
Session summary.
hello. Okay. So we have discussed about microscopic and macroscopic. So microscopic we discussed about, by particle level, the molecule level, and the macroscopic we discuss at, little bigger scale. So we assume that the things are continuous. Okay. So in microscopic description, I think someone is trying to say something. I don't know. So option B says the kinetic energy of a single molecule. So no, we don't discuss the kinetic energy of a single molecule in the macroscopic coordinate system. Not even in microscopic. In microscopic, we have a distribution. Okay. So these many particles can have this much kinetic energy. Okay. This much percentage of particles can have this much kinetic energy. Like that we discuss in the microscopic. For a single molecule, we don't discuss like that. And in macroscopic coordinate system, we don't discuss these things. Okay. The pressure exerted by the gas on the cylindrical wall. So this is the correct right option. Another option says the spin state of an electron. Again, this is not correct. And the last option says the velocity of a specific gas particle. Again, for a specific gas particle, we don't discuss in the macroscopic version. Okay. And in the microscopic version, we discuss some sort of, distributions. Okay. These many particles can have this much kinetic energy. These many particles can have that much velocity, like that. Okay. And the results of both of these three, macroscopic and microscopic, they ultimately will yield the same results. Okay. But in this course, we will mostly be focusing on the macroscopic version. Okay. So this is just like a definition. I don't think there should be any problem. The next question says, a rigid vessel contained a fixed mass of gas. Heat is added to the vessel, but no mass enters or leaves. This system is best classified as. So again, very easy question, definition based. We have discussed several type of system: open system, closed system, isolated system, control volume, adiabatic system, different types of system types. So you can easily answer this question, right? So which type of system this is? It is saying that mass transfer cannot take place, but heat transfer can take place. Okay. So in open
Option
system,
C.
yes, option C. In open system, mass transfer can take place. Okay. In an isolated system, there will be no interaction. Neither there will be mass transfer nor there will be heat transfer. Okay. In the closed system, we know that there will be no mass transfer, but heat transfer can take place. Okay, so for this particular vessel, it is saying that heat is added but no mass, so it should be a closed system. And control volume, again, it is more likely to be a open system. Okay, third question says, here's some statement. It is saying that if two systems are separated by an ideal adiabatic wall, their thermodynamic coordinates can change spontaneously until thermal equilibrium is achieved between them. Okay, so there are two systems, system 1 and system A and system B, and in between there is a adiabatic wall, and they can be at different temperatures initially. And since this wall is adiabatic, so there will be no heat transfer, so they will never come at the same temperature. Okay, so thermal equilibrium will not be reached, so it should be false, right? I think these questions are very easy, so you can suggest that we should discuss little more advanced questions, or we can keep this level, or we can little dilute the level. Okay, so as per your suggestions, I will make the questions accordingly for the next session. Okay,
We need to improve, I think.
sure, sure.
You can dilute this question.
So from next session, I will try to bring a little more conceptual questions. Okay, so fourth says that there are two systems, A and B, both are isolated from each other, but they are in thermal equilibrium with a third system. Third system is C. According to the zeroth law of thermodynamics, system A and B must have the same internal energy. System A and system B are in thermal equilibrium with each other. Third option says that both of the system A and B must contain the same working substance. And the last option says that both of the systems will exchange heat if connected by an adiabatic wall. So again, this is zeroth law of thermodynamics. So two systems, A and B, they are in equilibrium with C. Okay, so again, both of these should be in thermal equilibrium as well, right? So that is what zeroth law of thermodynamics says. So option A says that they will have same internal energy. This is not correct, right? Because they will have the same temperature, and internal energy per unit mass will be same, but the total internal energy can be different, right? If the system A is bigger and let us say B is smaller, even if they have same temperature, they can have different internal energy. Okay, so option A is not correct. Option B says that both of these systems will be in thermal equilibrium with each other. So this is correct because both of these will have equal temperature, right? And option C says they will contain same working fluid. It is, not correct. They can have different working fluids. And last option says they will exchange heat if they are connected by adiabatic wall. So if they are at same temperature, then why there should be any heat transfer? And even if they are at different temperature and the wall is adiabatic, again, there will be no heat transfer, right? So only option B is correct in this case. Okay. And fifth option says that for a simple compressible system, the equation of state relates pressure, volume, and temperature. How many of these coordinates are truly independent? So you might have studied about Gibbs phase rule, right? So if there is some, phase, and there can be some independent chemical components, and how many independent thermodynamic variables are there? So this Gibbs phase rule is the relation among these variables, right? So for this simple compressible system, how many independent variables are there? So Gibbs phase rule, if I write, it is, sorry, F is equal to C minus P plus 2. Okay. So F is basically number of independent variables, or you can say the degree of freedom. So degree of freedom is nothing, you can say it is the number of independent variables, or you can say it is the degree of freedom. C is number of chemically independent components, number of chemically independent components, and P is number of phase. Phase means there can be some liquid phase, vapor phase, okay, like that. So for a simple compressible system, there is only a single phase, okay. So P is equal to 1, and let us assume there is only one chemically independent component. There is any gas or there can be some mixture, but the chemical composition is fixed, okay. The chemically independent components is, let us say it is 1. So C is again, let us say 1. Okay, it is saying simple compressible system. Okay, so simple compressible system, you can assume like there is some system, piston cylinder arrangement, there is some gas, let us say oxygen is there. So this is a simple compressible system. So F you can easily tell now. So C minus P plus 2, so it will be 1 minus 1 plus 2. Okay, so only two variables will be independent. Okay, so degree of freedom is 2. So here it is saying pressure, volume, and temperature. So can all of these three can be independent? Answer is no. Okay, so if you have any two of these, then you can find the third one from another two. Okay, so pressure, volume, and temperature, there will be interrelated, there will be some function. Okay, so either temperature and volume can be independent, or you can have pressure and temperature, then you can calculate volume, but there will be only two independent variables. Okay, so the answer should be option B. Okay, this is Gibbs phase rule, by the way. Okay, so I hope this is clear. If there is no doubt, then we will move to the next question. Question number 6. It is saying that the physical quantity identified as the ratio of the change of volume per unit volume to the change in temperature at constant pressure, it's called average coefficient of expansion, right? So, or expansivity, we can say. Okay, and how do we define that? It is already saying that per unit volume, so 1 by V, and change of volume per unit volume to the temperature. Okay, so del V by del T. So it is rate of change of volume per unit, with respect to temperature at constant pressure. Okay, so this thing. Okay, and we call this as expansion coefficient, or expansivity, you can say. So this was question number 6. Okay, now next question. Question number 7, it says that the isothermal compressibility of a gas is defined mathematically as. So this is again a definition. Okay, so we have already discussed these things in lecture. Okay, so which option is the correct one here? In the previous one, it was change of volume per with respect to temperature per unit volume at a given pressure. Here it is
Option A.
Yes, option A, rate of change of volume with respect to pressure at a given temperature and per unit volume. Okay, and there is a negative sign. Why there is a negative sign? We know because that if we increase the pressure, then increase in volume will be negative, or we can say that if we increase the pressure, then volume will decrease. Okay, so this quantity will be negative. And if we are putting a negative sign just before this 1 by v, so this will make this k positive. Okay, so this will ensure that this coefficient is positive. Okay, but here in the case of uh, coefficient of expansion, there was no negative sign. Okay, now coming to the next question, question number 8. Question number 8 says calculate the isothermal compressibility. So compressibility, this thing, right? K is minus 1 by v del v by del p at constant temperature, right? For an ideal gas at a pressure of 0.8, and we have to tell our answer in atm to the power minus 1. So it is saying ideal gas, right? Ideal gas. So for ideal gas, what we have? We have PV is equal to RT, right? This is ideal gas equation. So what we have to find? We have to calculate the isothermal compressibility. We have to calculate K. Okay, to calculate K, we will have to calculate this quantity, right? So first of all, let us try to calculate del V by del P at constant temperature. So how will we calculate? So we have this ideal gas equation PV is equal to RT. We can write V is equal to RT divided by P. Okay. So if you differentiate this V with respect to P, we differentiate this V with respect to P at constant temperature. So what will we get? We will get RT divided by P square minus 1, right? So it is like differentiation of 1 by X with respect to X, right? So what we get? We get minus 1 by X square, right? So it is like that. And we need to multiply this thing by minus 1 by V, okay? Because K is minus 1 by V times 1 del V by del P times at constant temperature. So this thing we have already calculated. So minus 1 by V times minus RT by P square, correct? So what we have? We have RT by V P square, right? And RT from the ideal gas equation from here itself, we can write PV, right? RT we can write PV. So V R square. Sorry, this was P square. This was P square, not R square. This was P square. This was P square. So V and V, they will cancel out. And what will you get? We will get K is equal to 1 by P. Okay. So K will be 1 by P. And P here it is given, P is equal to, it is given 0.8 atmospheric pressure. So K will be 1 by P, that is 1 by 0.8. So you can calculate, this thing will come out to be 1.25 into the minus 1. Okay. So this is the answer. Okay. Fine. Hello. So in this question, what we had an ideal gas. So let us say if I say that this is not ideal gas, this is some other gas, and for that gas we have some other equation of state, then how will we proceed? Okay, let us say we have some other equation of state. Let us say another example, and some other equation of state that can be like van der Waal equation. Then how will we proceed? Hello. So if we have van der Waal equation, let us say, then we can write P is equal to RT by 1 minus, sorry, A minus B minus A by V square. Okay, I have just little manipulated the equation so that we get the expression for P. Okay, then what will we do? We will have to calculate this quantity, right? Del V by del P. Okay, but we have the expression for P. Okay, so what can we do? We can calculate del P by del V at constant temperature. Sorry, at constant temperature, and this we know this is reciprocal of this del V by del P at constant temperature. Correct? This is from this reciprocal rule, right? I hope you have studied these reciprocal rule, cyclic rule, and little bit of partial derivatives, right? So we can calculate this del P by del V. Should we proceed, or I should leave this?
You can leave.
Yes, sir, you can proceed.
Okay, I'm just given an example. Like in the previous question, it was ideal gas. So if it is not ideal gas, then how will we proceed? Okay, so let us try to calculate del P by del V at constant temperature. So first thing is, have I missed something? It is not A, it is V, right? Okay, so if we try to differentiate the first term, what will we get? We will get RT divided by V minus B squared. There will be one negative sign, right? So this is the derivative of the first term. Then the derivative of second term, it will be 1 minus V square ki jagah pe V cube, and this negative sign will make it a positive, and there will be 2, right? Power will come out as a coefficient. Okay, so like that. And since we know that del V by del P at constant temperature, this will be simply the reciprocal of this thing, reciprocal of del P by del V at constant temperature. Okay, so we can write this K is equal to minus 1 by V and this thing, right? 1 by del P by del V at constant temperature. And this del P by del V at constant temperature we have already calculated. So what will we get? We will get 1 by V whole thing divided by minus RT divided by V minus B square plus 2A V cube, right? Correct. So this will be K if we use this van der Waals equation instead of this ideal gas equation. Okay, so this is just an example. So we can have some other equation. There are a lot of equations for equation of state, right? Not just ideal gas equation or van der Waals equation. So for a given equation of state, you can find what will be the expression for this K, right? You can find the isothermal compressibility formula. Okay, for any given equation of state. Okay. So now proceeding to the next question. Question number 9. It says that in a quasi-static process, the system remains infinitesimally close to a state of. Option A says non-equilibrium. Option B says thermal imbalance. Option C says thermodynamic equilibrium. And option C says chemical reaction. So again, definition-based equation. So a quasi-static process remains infinitesimally close to thermodynamic equilibrium. Okay. Question number 10. Question number 10 says on a pressure volume indicator diagram. So we know what is an indicator diagram. Indicator diagram is nothing but this PV diagram. Okay. So we call the PV diagram as indicator diagram. The area under the curve for a quasi-static expansion process variable represents. So what does this represent? We already know the area. Sorry, the area under PV curve. This will be integration of P dV, right?
Option C.
And so this will be the work done. First option, heat transfer, no. Option B says the change in internal energy, again, no. Third option says work done by the system. So this is correct. And total enthalpy, again, this is not correct. So option C. 11th question, it says which of the following expression correctly represents the work done during a reversible isothermal expansion of an ideal gas from volume V1 to V2? What does this say? Correctly represent the work done during a reversible isothermal expansion process.
Option C. Option D.
Option
D, sir.
D. Okay, we have what we have work done is equal to area under the curve, or you can say integral of PdV. Okay, it is saying ideal gas. So this is work done, number one. Number two, it says ideal gas. So PV is equal to RT. Fine. Third, what does it say? It is saying isothermal. Okay. Isothermal. So isothermal means T is constant. Okay. Since T is constant, you can say PV is equal to RT. R is already constant, T is constant. So the PV is constant. Okay. And this constant you can write any constant. Let us see, it is C. So P, you can write some constant divided by V for a isothermal process. And for work done, what we have, W is equal to integral of PdV. Integral of PdV, and P we can write some constant divided by V dV. It's integration from state 1 to state C. Okay. So integration of 1 by V with respect to V, it will be ln logarithmic log of V. Okay. And this constant C, this will come out, right? This will come out, and we will have some limit of integration. Okay, limit of integration. So limit V1 to V2, right? And this will be C times ln V2 minus ln V1. And you know the properties of logarithmic. So if there is log A minus log B, you can write that as log A by log B, correct? So this work done will be that constant times log of V2 by V1, correct? और ये C जो है, what was C? C was this thing, PV, that is equal to RT, that is constant. Okay, so you can write W is equal to P1 V1 ln V2 by V2, that will be equal to P2 V2 ln V2 by, sorry, V2 by V1, that will be equal to RT ln V2 by V1. Okay, so all of these three are fine. Okay, so which option now? Option A, no, this is not correct. Option B, it says P1 V1 ln V2 by V1. This is correct. Third option says W is equal to 0. Again, this is not correct. Fourth option says P1 V1 minus P2 V2 divided by n minus 1. Again, this is not correct. So only option B, second option is correct. Okay. So again, in this question, it was given that this is a ideal gas. So we have the equation for ideal gas. If it was not a ideal gas, if it was something else, or you had some other state relation, then you will use that particular relation for pressure and volume. Okay, in this particular case, we have used this particular relation between pressure and volume. If there is some other relation between pressure and volume, we would have used that relation. Okay. And in that relation as well, since it is given it is isothermal, so we will assume T is constant. Okay, so that's what isothermal means. Okay. Now coming to the next question, question number 12. It says that for a closed system that undergoes a cycle, the cyclic integral of heat transfer is equal to the cyclic integral of work transfer. So we know that a cycle means that we are coming back to the same state with which we started with, right? And we also know that heat transfer del Q is equal to some work done plus change in internal energy. Okay. For a cycle, this del U will be 0, right? Because again, we are coming to the same point. Okay. And this internal energy is a point function. Okay. So there will be no change in internal energy if we are coming back to the original state. So del Q, this will be equal to del W, right? So the cyclic integral of this heat transfer, this will be equal to cyclic integral of this work transfer. Okay, so this is true. Now coming to the next question, question number 13. Question number 13 says the internal energy U is a thermodynamic property. Okay, ये thermodynamic property है. Work and heat, they are not property. Okay, so we should be very clear what is property and what is not a thermodynamic property. So thermodynamic properties, they are point functions, and the point functions, they have exact differentials. Okay, and what we mean by exact differentials, so for that we have very clear mathematical expressions. Okay, so that I hope you have studied. If we have not studied, then we can discuss now or maybe later, but those things should be clear. Okay, so mathematically this means that an infinitesimal change in the internal energy du is what? I said that all the thermodynamic properties, they have exact differentials. So since it is saying that internal energy is a thermodynamic property, so it should have an exact differential. So option A says inexact differential. This is not correct. Option B says path dependent function. This is not correct. Third option says an exact differential. This is correct. And option C says always equal to 0. This is not correct. Okay. So if a function, let us say Z is a function of X and Y. Okay. Then you can write the differential of Z, what it will be? It will be differential of Z. This will be equal to partial derivative of Fx with respect to X at constant Y times dx plus partial derivative of F with respect to Y at constant X times dy. This is the differential of Z. Okay, this is the differential of Z. And what we mean by exact or not exact, for that also we have a definition. Let us say that we can write Z is equal to something times dx, right? Here what we have? We have this something times dx and something times dy. Okay, so Z is equal to this something m dx. Okay, m times dx. This m can be the function of x and y again. Okay, this can be function of x and y again, plus again some other function that can be again the function of x and y times dy. Like that we write the differential. Okay, so if Z has exact differential, sorry, then it should satisfy this property. Which property? The derivative of m with respect to y at constant x, this should be equal to derivative of n with respect to x at constant y. Okay, so if it has an exact differential, then this relation should be followed. Okay, and how we defined the differential? We defined the differential as this: dz is equal to, if the z is function of x and y, like that we defined this differential. Okay, so if you compare this equation with this equation, then what we have this equation, these two equations. What we have, m is equal to del f by del x, and n is del f by del y at constant x, and this is at constant y. Okay, then del m by del y at constant x, this will be what? This will be partial derivative of f, and it is already the partial derivative with respect to x, and now you are differentiating with respect to y. Okay, with respect to y. Okay, this should be equal to del n by del x at constant y, and that will be equal to partial derivative of this thing. Okay, so what we have that if a function has exact differential, then the order in which we are differentiating, that should not matter. Okay, first you can differentiate with respect to x, then you can differentiate with respect to y, or first you can differentiate with respect to y, then you can differentiate with respect to x. In both cases you will get the same value. Okay, so if this thing is followed, then we call that this is exact differential. If this is not followed, then we call it is not exact differential. Okay, so if it is followed, then what will happen? You can take some example. Right now I'm not doing, but you can think it yourself, that you can take a closed path. Okay, and let us say this is point A and this is point B. Okay, this is x-axis, this is y-axis. Okay, so at all the points you will have some value for z. For example, at point A, let us say coordinate is x comma y. So at point A you will have some value for z. Okay, here the value for z will be something in terms of x and y. If you move a little bit in direction of x by dx, then here the coordinate will be x plus dx and y. So at this point you will have some other value of z, right? And then if you come to point B, then you will have some coordinate like this, x plus dx comma y plus dy, and here you will have some other value for z. Okay, from this path you are coming. Okay, from this path you are coming, then you will get some value for z at point B. Okay, so you can calculate what is the difference between the value of value of z at point A and point B. Okay, so when you go from this path from point A to point B, you will get some differential for z. Okay, so for this path you will have some value. Okay, let us call this point, let us call C. So if you go A C, so if you go like A C B, you will get some differential for z. Okay, let us say this is dz using this path A C B, and if you follow another path, this path, you are going from A, then D, then B, then you will add some other differential for z that you can call ADB. Okay, so if this property is followed, then you will find that this change in z, or you can say the differential of z along both these paths, this will be same. Okay, so you can say that this z is not dependent on path, because along both paths it is depending only on the initial and the final points. Okay, so I hope you are getting what I'm trying to convey. Okay, and if it is not followed, if this thing is not followed, then you can prove that if you go from path ADB, then differential will be something else, and if you go from path ACB, then differential will be something else if this thing is not followed. Okay, so can you prove this? This is very, I mean, an easy example I have taken. Okay, just a rectangle. Okay, you could have taken some arbitrary or some random path, but I have taken a very specific path, a very simple path, so that you can try to calculate this differential along both these paths yourself. Okay, so I am giving this to you just to convince yourself that yes, if this property is followed, then Z will be a point function. It will not depend on path. Okay, so you can note it down. You can try to do it yourself. And I hope this is a very simple problem. And if you find any difficulty, we will do in the next session. I am leaving this for your practice. Okay. Is this clear what I'm trying to convey and what is the problem statement right now?
Yes, definitely.
Hello?
Yes, definitely. Hello.
I'm just trying to give a feel. What do you mean by exact differentials, not exact differentials? When we say it is dependent on path, when we say it is not dependent on path, what is the meaning of differential? Okay. So if that is clear, then we will move to the next point. If you have any doubt, then please ask. Okay.
You explained very
Yeah, it is clear, sir.
Okay. So please try to calculate this dz along both paths and check that if this property is followed, this particular property, this exactness definition is followed, then you will see that this dz is same along both paths, otherwise it is not same. Okay. You can use the Taylor expansion. Okay. I'm just giving a hint. Okay.
Taylor expansion series. Yes.
Anyways, I hope you get what I was trying to convey. Okay. Now coming to the next question, question number 14. It is fill in the blanks. The work done by one part of a system on another part of the same system, like interaction of atoms or electrons. This is called internal work, right? Because they are the internal part of the system. So this should be internal work. Okay. And the total work done as the internal work, if you sum all those internal works, then this would be 0. Okay. Now coming to the next question, question number 15. It says that a composite system consists of two gas-filled chambers separated by a rigid diathermic wall. Okay, so diathermic means that heat transfer can take place. Okay, so this is a thermally conducting wall. They are separated by this type of wall. If the chambers have coordinates P, V, and T, and the another chamber has the coordinates P dash, V dash, and T dash. I think temperatures are same. Okay. What is the total work done by the composite system? What? It is saying what is the total work done by the composite system for the small displacement dV and dV prime. So again, this is very easy question, right? So we have two chambers. For first chamber, the coordinates are given like P, V, T. Okay, so for this particular chamber, this small work done, this will be P dV, right? And for another chamber, the coordinates are given like P prime, V prime, and T. So for this particular chamber, the work done will be how much? P prime
D prime.
times dV prime, right? So the total work done will be what?
It will be PdV.
Total dW will be P dV plus P prime dV prime. Okay. So option B should be the correct option. Okay. Now question number 16. Which mode of heat transfer is governed by the Fourier law and depend only on the thermal conductivity of the material? Natural convection, forced convection, thermal radiation, or heat conduction? So we know that this is
Conduction.
simple heat
Yeah,
conduction.
conduction.
Heat conduction. And what will be the rate of heat conduction?
K dt by dx.
K dt by dx per unit area, right? If you also multiply the area, then you will get total heat transfer rate, right? This is Fourier law. Now coming to the question number 17. This is regarding radiation, right? So it is saying, according to the Stephen-Boltzmann law, the radiant existence of a black body is proportional to basically the radiation heat transfer rate it is asking. So we know that this is, what is Stephen's law? The rate of heat transfer is equal to
T raised to 4. Done at T raised.
some proportionality constant, let us say that is sigma times 2 to the power 4. Okay, and all these temperatures are in Kelvin. Okay, so wherever it is not mentioned, you should keep in mind that everywhere it is in Kelvin. Sometimes when you are calculating temperature difference like that, okay, so sometimes we can take in Celsius as well, but in general you should take always in Kelvin. So option A, B, C, the temperature difference, the square of the absolute temperature T square. Option C says the fourth power of the absolute temperature T to the power 4. So this is correct. And last option says the inverse of absolute temperature. So again, this is not correct. Okay, so third option only. Now coming to question number 18, it says to calculate the power required to accelerate a 900 kilogram car from rest to a speed of 80 kilometer per hour in 20 seconds on a level road. So level road means height is not changing. So potential energy will be constant. Potential energy change will be 0. So only kinetic energy will change. Okay. And initially kinetic energy was 0. And finally, after 20 seconds, the kinetic energy will be 80 kilometer per hour. First of all, we should convert this 80 kilometer per hour into meter per second. So if you convert this thing to meter per second, it will be 18 times 1000 divided by 3600, right? Meter per second. And I will use calculator. It is coming out to be 22.22. Is it correct? So initially the kinetic energy is 0 and finally kinetic energy will be this half mv square. Okay, so the change in kinetic energy will be 1 by 2 this 900 kilogram times 22.22 meter per second squared. Okay, so these many joules we will have. So I will put the direct values. You can cross check the calculations. If there is any miscalculation, just let me know. Okay, so this is the change in kinetic energy. And we will assume that the power is constant throughout these 20 seconds. So the power will be what? The power will be rate of change of this energy, right? Power is work upon time, right? And the work, whatever work is being done, that is being converted into kinetic energy, right? We are assuming that temperature is remaining constant. Okay, so whatever work we are transferring, all of that work is being converted into kinetic energy. Temperature is constant, so internal energy is not changing, and we are assuming that we are not providing any heat. Okay, at least that form of heat, not in the, I mean, not as an external heat. Okay, whatever we are providing, we are providing some work. Okay, so this will be 22.2 kilojoule divided by 20 second. So what will we have? We will have 11.11 kilowatt. This will be the power. Okay. Now coming to the next question, question number 19. 19 question number says a person standing in a breezy room. Okay, so there is some air flow at 20 degrees Celsius. Okay, the exposed surface area of the person is 1.6 meter square and their average outer surface temperature is 30 degrees Celsius. The convective heat transfer coefficient is 6 watt per meter square Kelvin. The emissivity is 0.95 and the Stephen Boltzmann constant is 5.67 10 to 10 to the power 8 watt per meter square Kelvin to the power 4. We have to calculate the total rate of heat transfer. So the total rate will be, here we have both convection and radiation. So total heat transfer from the person in watt. Okay. So it is again very simple question. You can calculate what will be the total heat transfer in terms of because of this radiation, and what will be the total heat transfer with because of this radiation. Okay. So because of this convection, what will be the heat transfer rate? This will be heat transfer coefficient, convective heat transfer coefficient times this area times the temperature difference. Okay. The temperature difference delta T will be 30 degrees Celsius minus 20 degrees Celsius. So 10 degrees Celsius. Okay. And temperature difference you can write in Kelvin or centigrade, both are same thing because we are talking about difference. Okay. And heat transfer coefficient is given, area is given, temperature difference we have 10. So you can calculate heat transfer rate because of convection. And because of radiation, what will be the heat transfer rate? This will be sigma T1 square minus T2 square. Okay. For a black body, but it is not black body. It is some what is given. Emissivity is given. Okay. So epsilon is given. So epsilon is given to be 0.95 and the sigma is also given 5.67 10 to the power minus 8 in SI units. And temperatures, you'll have to put the temperatures in Kelvin. Okay. Temperatures you'll have to put it in Kelvin, then we can find this Q radiation. Okay. And the total heat transfer rate will be.
Is it T1 raised to 4? 4 mean to the power 4, no?
4. Sorry. 4. Yes, thank you. So radiation plus convection, this will be the total heat transfer rate. Okay. One thing you should keep in mind that you should not make this mistake that you sometimes student write like sigma delta to the power 4. Delta, this is not correct. Okay. T1 to the power 4 minus T2 to the power 4. Okay. This is not correct. This is correct. Okay. I think this you can calculate by yourself. This is not a big deal. Okay. So now I think you can move to the next question. I will write the answer so you can check it yourself. So because of convection, it is coming. I'm writing the values. Convection, it is coming out to be 96 watt, and because of radiation, it is coming out to be 66 watt, and the total convection plus radiation, it is coming out to be 162. Okay. So you can cross check these values. So if there is any miscalculation or any mistake, just let me know. Okay. Okay. So question number 20. Okay, so all these questions are more like the revision, or you can say the basics of all these basic courses, thermodynamics, heat transfer. Okay. Question number 20. Now it is about second law, and you have studied second law, in form of two statements. One is Clausius statement, another is Kelvin statement, right? So it is this question number 20 is about Clausius statement of thermodynamics, second law of thermodynamics. So what does the Clausius statement says?
It will be for the refrigerators and heat pumps.
It says cyclic integral of dq by t should be less than or equal to 0.
That is inequality. Okay, that is Clausius inequality. That is correct. But the Clausius statement of second law of thermodynamics, that I am talking about.
Yeah, we cannot pump heat from a low temperature body to a high temperature body without any external.
Without any external, right? We can transfer heat from a low temperature body to higher temperature body, but we will require some external work, right? But without external work, we cannot transfer heat from lower temperature to higher temperature body. So that's what this Clausius statement says. And when we are transferring heat from a lower temperature body to higher temperature body, then basically we are talking about a refrigerator, or you can say we are talking about a heat pump. Okay. So this is more directly related to these heat pumps and refrigerators. And the Kelvin statement, that is another statement of the second law of thermodynamics, but both of these statements, they are equivalent. Okay, both of these are equivalent. Okay, and you can prove that, right? If any one of the statement is violated, then second one will be automatically be violated. Okay, okay, so relates primarily to the operation of. So technically, it will be applied to all the systems, all the machines, but more directly it is related to those kinds of machines which transfer heat from lower body, lower temperature to higher temperature. Okay, and those machines are refrigerators and heat pumps. Okay, fine. This is easy question. Now coming to the next question, question number 21. It says that it is impossible to construct an engine operating in a cycle that produces no effect other than extracting heat from a reservoir and performing an equivalent amount of work. This implies the impossibility of. It is saying that it is impossible to make an engine that will just take some heat from a reservoir and convert all that heat into work without rejecting any heat to a lower temperature thermal reservoir. It is impossible to make that type of machine. Okay. So if we somehow made that type of machine, then we will be violating which law? Second law of thermodynamics, right? And that type of machine, what will we call? That we will call perpetual motion machine of second kind, right? If a machine violates the first law of thermodynamics, then that machine will be perpetual motion machine of first kind. And if that machine violates the second law of thermodynamics, then it will be a perpetual motion of machine of the second kind. And it is saying that you cannot construct such machine which produces no effect other than taking heat from a reservoir and performing some equal work without rejecting any heat to the lower temperature thermal reservoir. This is the basically the second law. Okay. Okay, Kelvin's statement, right? This is basically Kelvin's statement. Correct? Option B. Because if an engine that violates Kelvin Planck statement, that machine will convert 100% of the absorbed heat into work. Okay, so it will have 100% efficiency. Okay, and that machine will be a second perpetual motion of second kind machine. And these perpetual motion machine don't exist. Okay, so I think and I believe that most of you are thinking that this is quite obvious that we cannot make this perpetual motion machine of second kind. But there was a time in history when people got the patent for such machines. Okay. Today we have studied thermodynamics and these things seems very obvious. Okay. So if some person come and says that, okay, I have designed a machine that will be just continuously running without any external energy source, or I have made a machine that has 100% efficiency. We know that it is not possible and it is very obvious to us. But at some point of time, people have got patent for such machines. Okay, and later it was proved that they are fake machines. Okay, they are doing some tricks. Okay, they have, for example, they have some hidden energy source. Okay. Anyways, so coming to the next question, question number 22. It is saying that Kelvin-Planck statement and the Clausius statement of the second law are logically equivalent. Yes, they are equivalent. So the violation of one statement will be the violation of another one. So again, this is right.
True.
Okay, so we have to tell true or false. This is true. Okay, question number 23. It is saying which of the following is not a cause of irreversibility in a thermodynamic process. So it is saying solid friction. So we know that all sort of frictions, they cause irreversibilities. Option B says
Option C.
unrestricted. Okay.
Option C
Let-
is option C.
Okay. Option B says unrestricted expansion of gas into vacuum. So again, this is irreversible process. Okay. And how much irreversibility is involved? How much is the that entropy generation that we can calculate? I think we will do that in next session. But we know that unrestricted expansion of gas in vacuum is a irreversible process. Anyways, third option says infinitesimally slow heat transfer across a zero temperature difference. So this is correct option. Okay, so this we can consider as a reversible process. Okay, so this will not cause any irreversibility. So, but if there was a finite temperature difference, then there will be some entropy generation. Okay, and how much entropy generation will be there, that we can calculate. Okay. Option last option says electrical resistance. So electrical resistance, we know that those electrical resistance, they will convert work or electrical energy into heat. Okay, and this electrical energy is a high grade energy and heat is a low grade energy. So all of that electrical energy can be converted into heat, into a low grade energy. But if you try to convert that heat into electrical energy, you will not be able to convert full heat. Okay, you will not able to convert all of that heat into electrical energy. Okay, you can convert some part of that, but you cannot convert all of that. Okay, because if you try to convert all of that, then you will be trying to violate the second law of thermodynamics, right? So this conversion is irreversible. Coming to question number 24, next question. It says the Carnot cycle consists of which sequence of reversible processes? Again, very easy. Carnot cycle, there are 4 processes. 2 of them are isothermal and 2 are adiabatic, right? So option says option A, 2 isobaric and 2 isoporic, wrong. 2 isothermal and 2 isoporic, again not correct. Third option says 2 isothermal and 2 adiabatic process, they are correct. This is correct. And last option says 2 isobaric and 2 adiabatic, again this is not correct. Okay. Carnot engine is such a engine which takes heat from a constant temperature reservoir and again reject some heat to again another reservoir at constant temperature, right? And we get the maximum efficiency, right? Because Carnot's theorem itself says that the maximum possible efficiency is limited by the reservoir temperatures. If we fix the temperature of the reservoirs, then we will be taking heat at constant temperature. We will be rejecting heat at constant temperature. Okay, so these are 2 isothermal processes. Okay, that's it. Then other than these 2 processes, there will be no heat interaction. So the remaining 2 processes will be adiabatic processes. Okay, so in the Carnot cycle, we have 2 isothermal and 2 adiabatic processes. Okay, now moving to the next question, question number 25. Okay, it says that according to Carnot's theorem, no heat engine operating between 2 given thermal reservoir can be more efficient, I think, more efficient than a reversible engine operating between the same 2 reservoirs. So this would be efficient, right? So Carnot engine is the most efficient one. Okay, so again, this is easy question. I think we can move to the next question. Now coming to question number 26. It says that the coefficient of performance of a heat pump and refrigerator, which are operating between the same temperature limits. What is the relation? What is the coefficient of performance of a heat engine? And what is the coefficient of performance of a refrigerator? So both of these are defined. What is our purpose? What purpose we are solving and what cost we are solving. Okay. So the purpose of this refrigerator is to remove the heat from low temperature reservoir. Okay. So purpose is to remove the heat from low temperature reservoir. So remove QL. And what is the cost? Cost is what external work we are providing. Okay, compressor जो अपन use करते हैं. So to that compressor we are providing some work. Okay, and that cost is that work that we are providing. Okay, so this is the coefficient of performance of refrigerator. And what is the purpose of heat pump? Heat pump basically tries to heat your room, heat your house. Okay, so basically we are adding some heat to a high temperature reservoir. Okay, so we are adding some heat to the high temperature reservoir. We are adding some QH to the high temperature reservoir. Again, we are providing some work in the form of compressor, W net. Okay. And this W net, we know this is what? This is QH minus QL, right? Correct. So QH, QH is basically W net plus QL, right? So for a case of heat pump, it will be QH, you can write W net plus QL divided by W net. Okay, so this will be 1 plus QL by W net. This is the coefficient of performance of heat pump. COP of heat pump. And COP of refrigerator is QL by W net. Okay, so if you compare these two expressions, you can clearly say that coefficient of performance of heat pump, this is 1 plus this another term, and another term is actually equal to coefficient of performance of refrigerator. Okay, so which option is the correct one? Option A is not correct, I think. Yes, option B, coefficient of performance of heat pump is equal to coefficient of performance of refrigerator plus 1. This is correct. Third option again not correct. Fourth is again not correct. So second option is correct. Okay. Now move to the next question. In a thermodynamic temperature scale, the ratio of heat absorbed to heat rejected for a reversible Carnot engine is equal to thermodynamic temperature scale means Kelvin scale. Right? The ratio of heat absorbed to the heat rejected. So heat absorbed, we take heat from high temperature reservoir. So that is QH, and we reject heat to a lower temperature thermal reservoir, that is QL. So the ratio of this QH to QL, this is equal to TH to TL, temperature of high thermal reservoir from which we are taking heat, and TL is the temperature of lower temperature thermal reservoir to which we are rejecting heat. Okay, so these two things are equal. Okay, so that's why the efficiency is the work output divided by how much heat we are taking. So that becomes equal to QH minus QL by QH, and that becomes 1 minus QL by QH. And since QL by QH are equal to TL by TS, so this efficiency in terms of temperature we write 1 minus TL by TH. Okay, so because of this relation only, this formula is possible. And actually, this is the way this temperature scale is defined. Okay, so this is intentionally defined like that. Anyways, so what it was asking? It was asking that QH by QL will be equal to what? So this will be equal to TH by TL, right? So option A is correct. Now we have few more questions. Let's try to solve them quickly. 28, it is saying the Carnot heat engine operates between a high temperature source at 600 Kelvin. Okay, so the temperature of high temperature thermal reservoir is 600 Kelvin. And low temperature reservoir sink, it is at 300 Kelvin. It absorbs 800 kilojoule. Okay, so QH, it is absorbing 800 kilojoule of heat per cycle. Calculate the thermal efficiency of engine. We just wrote the expression for thermal efficiency. It was 1 minus TL by TH. Actually, it was 1 minus QL by QH, but it eventually becomes, in terms of temperature, 1 minus TL by TH. Okay, so 1 minus 300 divided by 600, so it will be 1 minus 0.5. So 0.5 is the efficiency, or you can say 50%. Okay, very easy question. I hope there is no doubt. So we'll move to the next question. Question number 29. It says using the same parameter from 28. So, okay, same parameters means source at 600 Kelvin, sink at 300 Kelvin, and 800 Kelvin of heat is absorbed. Okay, so QH is 800 Kelvin. Calculate the net work output of the Carnot engine per cycle. Okay, so efficiency is defined as this net work output divided by how much heat is taken from the high temperature reservoir. And efficiency we have calculated was 0.5, or you can say 50%. This will be equal to the net work produced per cycle divided by the total heat absorbed per cycle. Okay, okay, this is not in Kelvin, this is in kilojoule. 800 kilojoule. So the net work output will be 400 kilojoule, correct? Okay. Again, very easy it was. Now, question number 30, it says a reversible refrigerator operates between a cold space at 250 Kelvin. So temperature of low temperature space is 250 Kelvin. And a warm environment. So the high temperature reservoir, you can say it is at 300 Kelvin. If the compressor requires 2 kilowatt of the power, okay, so the work net that you are providing to the compressor, this is 2 kilowatt of the power. What is the rate of heat removal from the cold space in this kilowatt? Okay, so this is a refrigerator, and coefficient of performance of refrigerator we just discussed. It was what? How much heat we are removing from low temperature reservoir, QL, at what cost? W net. Okay, correct. And QL, sorry, this W net is QH minus QL, right? So this will become QL divided by QH minus QL, and you divide numerator and denominator both by QL, so you'll get 1 minus QH by QL minus 1. And QH by QL you can write in terms of temperature as TH minus TL minus 1. Okay, I think, I hope you already remember the formula for coefficient of performance of refrigerator in terms of temperature. I am just writing so that if you forget, or if you asked to derive, you should be able to do that. Okay, so I am doing all these steps. Okay, so it will be equal to 1 minus TH. How much is TH? 300 Kelvin. And TL is 250 Kelvin minus 1. So the COP comes out to be how much? You can calculate this value. This is coming out to be 5. Okay. We will just cross check. So it is what? 1
It will be 5 only.
divided by 300 divided by 250 and minus 1. So it is coming out to be 5, correct? So yes, this is 5. And what we have to tell, the rate of heat removal from cold space. So the rate of heat removal from cold space, we have the formula COP of refrigerator is the rate of heat removal from cold space, that is QL divided by W net. And the COP we have calculated, this is 5. And W net is given how much? 2 kilowatt. So this QL will be 5 times 2 kilowatt. Okay, so this QL will be 10 kilowatt. Okay, so it is clear, I hope. So you don't need to memorize anything. If you already know the formula, it is well and good for you, because in exams or where you have some time foundation, it is always good to remember some formula and some expressions. But if you are asked to drive or you somehow forgot, then you can do step by step. Okay. So this was the last question. So if you have any doubt in the content of week 1 or the first assignment that you have got, or in this session, or any general discussion, or if you have any suggestion, then you can please tell. One suggestion I have got in this session, that we can make the questions little advanced. Okay, so that I will try to make sure in the next session.
Definitely.
So if you have any doubt, you can please ask.
Thank you.
So I think some participants have joined later. Banker Lang has joined later. Mohammad Rahman joined later. Pooran Singh joined later. So if you don't mind, you can please introduce yourself, because at the starting of session we had a little introduction session. So in that session we just introduced ourselves, what we are studying, and why we are doing this course, what is our expectations from this course. Okay. So hello. Yes, Pooran is saying something. I can't hear Pooran. I don't know why. So I think there's some issue. Rahman, you can please introduce yourself.
Hello, sir.
Yeah, good evening. Hello.
My name is Rahman, sir. I am student from the Usmania University of final year of mechanical engineering.
Okay. You are studying, undergraduate, or MTech or PhD, or
No, the final year of undergraduate, sir.
okay, BTech final year. Huh? Okay.
Yes, sir.
Okay, thank you. And we have Banker Lang. So you can unmute and introduce yourself. Hello.
Am I audible, sir?
You are audible.
Okay, sir. Very good evening, sir. I joined late because I came office evening and office after some late. That's why I got. So my thing is actually, sir, myself Puran Singh. I'm working in Bikram Sarabhai Space Center, and I'm doing this course because my guide told me to attend because I'm planning to attend get admission in the PhD program. So for the present guide told me I will be joining late, but you have to just show me some this coursework, background work, and then you have to come like that. He suggested, so that's
Okay.
why I joined this course, sir. So
Okay, so currently you are doing masters, right?
no, sir. I actually back the degree, so I have to do more course work. So that's why he's telling that it's really better you just get a one feel and do this course, and then you come. Especially, I'm planning to take in Combustion area. And
Okay.
so that's why it is. So this was the one topic or which subject was suggested by him. So that's why I am attending it, sir. I have
Okay.
just attended this some assessment sessions also. It was good, sir, because it is a like a combined thing, which is like thermodynamics plus your flame, the combustion area. So
Combustion.
that way.
Yeah, right.
So that way it is. Okay, actually, I am studying only. So it was good session. Whatever I think that questions are almost not the very depth, but some few doubts I was having, sir. This is some this sessions whatever is there, some any like recording or something will be there, or how is it means, or we have to fill somewhere to get our attendance. That was the one part. And
As far as I know, in the NPTEL sessions, uh, there is nothing like a an attendance like what we do in our
okay,
institutes.
sir.
But
Okay.
when you watch the lectures, you can see that it is showing your progress. So that you can consider as attendance for your purpose. But
Okay.
the important is that if you want to get a certificate from NPTEL, then you
Okay.
need to solve these assignments, and there will be an exam at the end of the course that you need to write that exam, and you need to register for the exam. Okay. If
Okay,
you
sir.
just want to watch the lectures and you want to just solve the assignments and you want to join these live sessions, for that there is no fees that you can do, I mean, free of cost. But if you want a certificate, then you will have to write an exam at end of that course, and for that exam you need to register.
Okay, sir. Thank you for that, your description or background of this. Already I registered, but this just because I don't know, because I'm appearing first time, so how I don't know what will the difficulty level of the written exam. So just if any some like some previous questions or something like some guidance can we get, or how we just, can you elaborate on that? Really good information to me.
Difficulty level you can expect similar to what you are doing in the assignments. Okay. So whatever we are studying, so everything should be related to that. Okay. I'm not saying that the questions that we are doing in assignment, the exact questions you should expect, but the difficulty level you can expect similar type of uh, difficulty. Okay.
Okay, sir.
And
Okay.
for exam
Thank you.
registration, you need to do that separately. And if you just want to learn and attend these sessions and solve assignments, then for that you don't need to do any special registration. But if you want to write exam, then you need to pay some exam fees. I don't know what is the exact amount, and you need to do uh, registration for the exam.
Okay, so that because since guide told me already, I registered for that, so I will be willing to write that exam also.
Okay. Okay. So if
Thank
you
you,
have
sir.
any suggestions for these live sessions, what should we, I mean, do? For example, today we just solve the problems. Okay, so if you
Okay.
have doubts in the lectures, in the assignments, so that we can discuss. Or if you have
Uh,
any suggestions, like we should
uh,
solve a particular type of questions, like many people prefer that we should do theoretical questions, because many of the students they are in like uh, institutes where they write exam in which the theoretical questions are asked. Okay, so
okay.
they sometimes expect they should do some theoretical question discussions. And many people who are preparing for these competitions, they will expect that you should try to do more of numerical, especially
Mm.
in the form of MCQs. Okay,
Okay,
so
sir.
some people may want that we should discuss more numericals. Some people may want that we should cover more conceptual concepts. Okay, so whatever your expectations are, that I will
I
try to incorporate,
Okay, sir. I think
and you can.
whatever I session I have done since I joined the session, it's a mix up, I think. So This is so well good, sir, for me.
Okay.
This is okay. Only thing just some this whether this whatever solved this presentation will be shared or to us or anything will be there, sir.
Yes, this whatever I have written here, this will be shared. Okay.
Okay.
So on the Swayam portal, you will get a option which says, I think, problem solving session, right? You have week
Okay.
1, then lectures, then week 2 lectures, assignments, and at the same place, I think you will get a option for problem solving session. So I
Okay.
think there you will get a link. So this is
Okay.
the first session. I will upload this, and also the recording I will upload in the YouTube, and the link will be provided in that section.
Okay.
Okay.
I think
So
this is okay, sir. So I think both mix up theoretical plus calculation based. Then I think that will be good, sir. For sure.
and if you have any query, you can discuss here, of course. But sometimes, because of any any reasons, if you are not able to join the session, I will encourage that we should join the session because it's live and we can have discussion 1-to-1. But you can
Sure.
also write in that Q&A section. I think there is a question answer section in the Swayam portal, right?
Okay, sir. Thank you, sir. Next time I will be trying to join on time. So,
Okay, no problem.
okay.
Sir, may I ask a question, sir?
Yeah, sure, please.
Sir, actually, in that first week lecture, we were repeatedly talking like hydrostatic system. Generally, we will be talking like thermodynamic systems. So why specifically here we are limiting to like hydrostatic system?
I will have to revisit that section where we are repeatedly saying this hydrodynamic system. In fact, when I was
Hydrostatic.
preparing hydrostatic, I was preparing this question number 5. It was saying that for a hydrostatic system, the equation of state, how many are these independent? But I intentionally changed that to simple compressible system, because most of the time we are saying simple compressible system. We don't want to limit ourselves to hydrostatic system, right? So I will go through that section and I will try to understand what is the context. Okay, then I can discuss in that in next section. Okay. Okay, I have noted down this query. Okay, why specifically hydrostatic? This is in which lecture 1, right?
Yeah, I think the whole lecture is mainly talking like properties or processes associated with hydrostatic systems. Okay, maybe he may be trying to simplify something,
Okay,
but I'm not sure what.
Okay, sure. I will try to get the context and we will discuss in the next session. Okay.
And one more thing is, in general, now the sessions, whatever we are having is almost 1 hour sessions. So I have attended some other courses also, where the duration is maybe some 30-40 minutes. So since this thermodynamics involves a lot of concepts, what I personally feel is we can have more number of lectures rather than some 3 lectures, can be 5 or 6. But if you can reduce it to maybe 30-40 minutes with more examples or something like that, then it will be more good, I felt.
Well, there are 2 types of things going on. I just one is recorded lectures and this is live session. Probably you are talking about the recorded lectures, right?
Recorded lectures, yeah.
Yeah, we can't change that because they are already recorded. Okay, so they will be floated as planned. Okay, but this live session, this is, I mean, I will try to make it quite flexible. So if you have any suggestions regarding this live lectures, duration, number of questions, type of question, that I will definitely try to incorporate. But those lectures are already recorded, so I don't think that there is much scope for any amendment.
Yeah, I was also feeling that like live sessions also. I am looking for a PhD, so I was thinking of more bit more complex, like conceptual things for the work also, related work also.
Sure, I will try to incorporate those things. Okay, we will have mixed type of questions, maybe some theoretical questions where we can discuss conceptual concepts related problems, some numericals, and some objectives, so that those who are preparing for competitive exams. So I think we should try to make it fruitful for everyone. Okay, so yes, sure, I will try to do that. Okay. Okay, so I think we can stop now, right? We will meet in the next session on next Tuesday. Okay.
Sir, one more doubt.
Yes, please.
What this periodicity will be? What means within 2 weeks, or what? Or every week will be there like these sessions?
This live session will be conducted every week on Tuesday. Okay, same time,
Okay.
6 p.m. to 8
Same
p.m.
time. Okay.
Yes, if there is any change, you will be informed via mail.
Okay.
But in general, this will be on Tuesday, 6 p.m. to 8 p.m. every week.
Okay, sir. Thank you, sir.
Okay, thank you.
Sir, I have one doubt, sir.
Uh-huh.
Sir, in the last question, can we display last question, sir?
Last question. Okay, this one, right?
Yes, sir. Sir, we want to calculate the rate of heat removal, sir.
Heat removal from the cold space, right?
So, sir, the rate of heat removal is how, sir? How the rate of heat removal is different from the cooling capacity, sir?
Cooling capacity means we have not said anything related to cooling capacity or any term like that. Rate of heat removal it is asking, and it is the ratio of heat removal, that is our purpose, right? So what is the purpose of refrigerator? It tries to remove the heat from cold, your freezer that is already cold.
Yes,
And
sir. That is
at
understood.
what cost we are providing some work, right?
Yes, sir. But rate of heat removal is how different from the cooling capacity, sir? I'm asking how cooling capacity is different from rate of heat removal, or both are same?
Cooling capacity, in which context you are saying? If you can tell, definition or little description of cooling capacity, then we can probably, I can understand better. Is there any specific term that is hard, very strictly defined as cooling capacity?
Yes, sir. In uh, refrigeration and air conditioning subject, we need to calculate the.
Okay. I will check if there is a specific term which says cooling capacity. I think it is there, but these terms are sometimes used very, lightly, and meaning becomes clear based on the context. Okay.
Okay, sir. It's good
I have
to
noted
when.
down both of these things. Why in the lectures we are repeatedly referring to hydrostatic and this cooling capacity. And cooling capacity, I suggested, is saying that the measure of how much heat an air conditioner or cooling system can remove from an indoor space over a specific period of time. Okay. So we will discuss this in the next session. Okay. Is I need to check what is the exact meaning of this cooling capacity is. Okay.
Sir, one last question, sir. One final question. Sir, in the conduction, Fourier law of conduction, sir, we are having some significant of sign, sir. This minus sign.
Significant of? I had written somewhere, right? Here, yeah. Okay.
Yes, here we are having some significant of sign, sir, due to
Sign.
the temperature difference. Minus K into T1 minus T2, right? We are writing like this.
because heat flows from higher temperature to lower temperature.
Yes, sir. The question is, why don't we have the sign signification, the convection law, sir? That we are
No,
calculating
it
the.
depends. You can put any sign. Okay. I mean, it should be clear to you whether your system is getting heat or it is losing heat. Okay. If your system is at higher temperature and your surrounding is at lower temperature and your system is losing heat, then if it asks that what is the heat added to the system, rate of heat addition, then we should get a negative sign, right? This sign and all these things, they are very, concept, depends on context, whether you should put this negative sign or not put. Okay.
Okay, sir. Okay, sir. No issue. No.
Because instead of remembering that negative sign is there or not there, it is always better that we should have a feel. Okay. So it is, if it is simply asking that how much heat is being lost per unit time from system to the surrounding. So if the system is at higher temperature, surrounding at lower temperature, then some finite positive amount of heat will be lost from system to surrounding. Okay. So the sign will be positive sign, right? If it is asked how much heat is being added to the system with the same, condition, then the answer should be in negative terms, right? So based on the context, it should be clear. You have to put the negative sign or not put, or instead of remembering what sign we are putting. Okay.
Okay, sir. No, sir. In some kind of university exams, the question will ask like, what is the significance of having a negative sign in the Fourier law of conduction? So, in that sense, I am asking to you.
So that is because the definition of that gradient sign. Okay. So what we usually do, we take, for example, this type of a system. Okay, this is x plus dx, and how we define gradient. Okay, so how some heat is coming from this side, some heat is losing from this side. Okay, so the temperature of this side is, let us say, T. Here the temperature is T plus dx, and then what will be the temperature gradient? Temperature gradient will be dx by
Dx by
uh,
dt by dx.
dt by dx. Okay, and some heat is coming at this point, some heat is going from this point. Okay, so at this point, how much heat is going? So at this point, heat is going dt by dx at this x. Okay, I'm not writing those coefficients. Okay, and at this end, heat, how much heat is being lost, that will be dt by dx at x plus dx. Okay, and the total rate of heat that is being added to the system, that will be how much? That will be dt by dx at x plus dx, sorry, minus dt by dx at x. Okay, and this change will be what? This will be derivative of this thing, dx dy dx of dt by dx times dx, correct? So this will be d square by dx square times dx, right? So this is heat that is being added to the system. Right? Hello?
Yes, sir. Yes.
So this is fine. I mean, where is the problem? I don't understand. So you just bring that particular question, or I mean, that type of thing, then we can have a better clarity what the real doubt is. But I think I got your point, that there are sometimes they are putting the negative sign, sometimes they are not putting the negative sign. Okay. So my suggestion is that you should have a feel. Okay. Your intuition should work. and you should know whether it is asking how much heat is being added and how much heat is being, taken out. Because like I remember in, in class 12th, in chemistry teacher, they were putting a negative sign, physics teacher, they were not putting a negative sign for the work done formula. You remember that? So
Yes, sir. Yes, sir.
it is all about the definition. Okay. Okay. Probably you can discuss it in more detail, but that will require some additional time. Okay, should we stop now or?
And sir, is it possible then bring some question related to the engine connected in series, sir?
Related to what?
Engine connected in series, sir.
Engine?
Connected in series.
Engine connected in series. Hello?
Yes, sir. Engine connected in series, sir. Some kind of a problems are given in the assignment in the thermodynamics course. And
Okay, sure. I will try to bring. And if it is in the, course content, then probably we should try to discuss during those lectures. If it is already discussed in lecture, then in the session it becomes easier, and it also becomes easier to understand if you have already, watched the lectures. So if it is not there in lecture, then we can discuss that separately here. But if it is there in the lectures, then we will try to discuss in that particular session. Okay. So if it is
Okay.
asked in the assignment or what?
No, sir, not in the present assignment, but in related to this course, sir, thermodynamic course and like this.
Okay, sure.
So if you are discussing the engine problem, then please do that. I'm just suggesting, not
Sure.
demanding.
I thank you for your session. I will definitely include that. Okay.
Okay, sir.
Okay.
Okay. Thank you.
Okay, thank you. Okay. So thank you all. Good evening. And now we will meet in the next session.
Okay, sir. Thank you, sir.
Thank you.
Thank you, sir.